In this set of notes, we're going to continue looking at multiple linear regression. So this first page should be reviewed from earlier in the semester, so I'm going to let you read this first page on your own, but it's talking about the difference between quantitative and categorical variables. So when we talk about our independent variables, remember that independent variable is the same thing as an explanatory or a predictor variable. That all means the same thing. They could be quantitative or categorical. So far we focused on quantitative, but in this set of notes we're going to look at categorical variables. So again, I'm going to have you read this first page on your own. Alright, so we're going to start by looking at models with one qualitative or one categorical independent variable. So again, up to now we've focused on the inclusion of quantitative predictor variables in multiple regression. Now we're going to consider the case in which we have a qualitative or again a categorical variable. So recall that a dichotomous variable is very common. These are variables that are often coded as a 0 or 1, and we could call them dummy or indicator variables. So for example, we could include a variable for whether or not a patient survives by using the following dummy variable. So we're going to let x1 be equal to 1 if the patient is alive and 0 if the patient is dead. And so we could consider the following model that we have here. So the expected value of y is equal to beta naught plus beta 1 x1. So notice this looks very similar if we just looked at the model to when we looked at simple linear regression. But the big difference between what we saw before is now that x1 is categorical. It only takes one of two values. So let's look at what happens when we look at the two different potential values for x1. So the first thing we're going to do is we're going to look at what happens to the expected value of y if a patient survives. In other words, if the patient is alive. So in this case, notice what we're going to have. We're going to have beta naught plus beta 1, and x1 is equal to 1 in this case, so multiply by 1. So we get beta naught plus beta 1. So we can denote this as mu a. In other words, this is the mean for when the patient is alive. On the other hand, if the patient dies, we have the following. So we just have the intercept term. So notice the difference between these is really the beta 1 term. So what beta 1 is doing is it's measuring the mean difference in survival. Okay? So that beta 1 term is really what's telling us about the mean difference between the two different possible values for x1, in other words, the 0 and the 1. And really what is going on here is we're really creating two separate lines. We're creating one line for those that survive, or that are alive, and one line for those who die. Now we're not limited to dichotomous variables. We could look at categorical variables that have more than two options. And so we can do this by adding on more dummy variables. So let's consider a variable for eye color, blue, green, or brown. And we can account for this by looking at two different dummy variables. So notice that we've got x1 is equal to 1 if the eye color is blue, x2 is equal to 1 if it's green. And you might say, well, how do we account for brown? Well, notice if both x1 and x2 are 0, then we have brown. So in this case, brown is known as the base case, and so we're going to look at what that means. So consider the following model. Notice again, this looks similar to what we've seen before, but the big difference here is that x1 and x2 are dummy variables, or we could call them indicator variables, and what they're doing is they're helping us code the categorical variable eye color. So let's look at what happens when the eye color is blue. So we're going to have beta naught plus beta 1. Now when the eye color is blue, x1 is equal to 1 plus beta 2. And notice x2 is only equal to 1 if the eye color is green. So if it's blue, x2 is 0. All right. Now we could do something similar to for green. So notice for green, we're going to have the following. And for brown, we have the following. So in terms of eye color, in terms of the mean value that we would see for y for the different eye colors, first of all, notice that the brown, so the mean response for brown is just equal to the intercept. Then what I could do is maybe I want to compare the difference in means between different eye colors. So for example, I might want to look at what is the difference between those that have blue eyes and those that have brown eyes. Well, notice in this case, if I take what I got for blue, which is beta naught plus beta 1, minus what I had for brown, I'm just left with beta 1. And then I could do the same thing for the green. So I could look at the mean difference between the green and the brown, and I would get the following. And so by looking at this, really what this is doing is this is helping us find the interpretation of our coefficients. So if we look here, notice that the intercept, what the intercept really does is it tells us about the mean for our base case. Beta 1 is telling us about the difference between the mean for the blue and the mean for the brown. And beta 2 is telling us about the difference between the mu for the green and the mu for the brown. So in other words, beta 1 and beta 2, what they're doing is they're comparing our other two cases to our base case, which is brown. So when you code your dummy variables, it's always important to note which one is the base case. So in this one, brown is the base case. And the reason for this is the coefficients are always going to be giving you that comparison back to that base case. All right, and so here that is summarized. All right, so when a qualitative variable, or we could call this a categorical variable, has k categories, we need k minus 1 dummy variables. So here we have a procedure for creating dummy variables for a single categorical predictor variable with k levels. So notice here we have our model, and so you'll notice in terms of our x's and our betas, we only go up to k minus 1 because we're going to have k minus 1 dummy variables. And then what we do is we're going to have k minus 1 xi's. So for example, x1 is going to be equal to 1 if the categorical variable at level 2, when we have that categorical variable and 0 otherwise. So this is very similar to the eye color example. So what we were saying there was brown was the base case, so x1 was for blue. So x1 would be equal to 1 if the eye color was blue and 0 otherwise. So the number of dummy variables for a single qualitative, or again we could say categorical, is always 1 less than the number of levels for the variable. Then, assuming the base level is A, the mean for each level is as follows. So this right here is exactly what we just showed with the eye color example. And it ends up, if you're familiar with an ANOVA test, you actually get the same results as an ANOVA test. So if you look at a one-way ANOVA, where you looked at the difference in means for a categorical variable, you could equate these two methods and you would get similar results. Alright, so let's look at an example. So we have data from 113 hospitals in the United States were used to assess factors related to the likelihood that a hospital patient acquires an infection while hospitalized. The variables here are as follows. So our response variable is going to be infection risk. And the predictor is an indication of which of the 4 U.S. regions the hospital is located, whether it be northeast, north central, south, or southwest. So notice here we do have a single categorical predictor variable with 4 levels, so we know that we are going to have to create 3 dummy variables when we fit this model. So the focus of the analysis will be on regional differences. So region again is a categorical variable, so we're going to use those indicator or dummy variables to incorporate the region information into the model. So here we have our dummy variables. Notice there are 3 of them. So region 1, which in this case is, actually we're going to label west as the 1. This is going to be our base case. Okay. And so here are our 3 dummy variables. So here's our R output. So notice here, if we look at our factors, notice that I have my beta hat 1, beta hat 2, and beta hat 3. So in other words, I have the estimates of my coefficients for each of my 3 dummy variables. So when you fit these in software, do be very careful, because software will often automatically choose which one is the base case, and this will depend on how these are entered in the data set. So for example, if your factors are entered as their names, most software will use the one that occurs first alphabetically as the base case. Or if your variable is entered as, let's say, 1, 2, 3, and 4, in this case, it will choose the first one numerically as the base case. Now you can coerce software, and tell it which one you want the base case to be. It actually doesn't matter which one you choose to be the base case when fitting your model. The only thing that's going to change there is how you interpret your coefficients. So it doesn't change the actual outcome or the actual results, but it will change the interpretation. And the reason for that is remember that all of the coefficients are always going to be in relation to what the base case is. All right. So the first thing we're going to do is we're going to propose a model for the mean infection risk expected value of y that will allow the researcher to compare the hospital region. So we have the expected value of y. We're going to have our intercept term. And again, remember that we had 4 different hospital regions, so we had 3 dummy variables. So we're going to have the following. And then whenever you propose the model, even though we have it up above, it's always a good idea to go ahead and redefine what those variables are so that we're very clear. So in this case, our base case is the west region. So for x1, we've got x1 is equal to 1 if, and let's go back up and double check our model. So remember that x1 was region 2, which is northeast. Zero otherwise. Looking at x2, x2 is region 3, which is the north central. And again, 0 otherwise. And then x3, that one was the south. And again, 0 otherwise. So, do the data provide sufficient evidence to indicate that the mean infection risk differs by region? Notice that this question is very similar to a question that you could solve using an ANOVA test. And again, you would get the same results from the ANOVA test as we are from this method. All right, so our model only has a single categorical predictor, so this is the same thing as looking at the overall model. As always, remember that you have to check those assumptions. We're going to learn how to fully check those later on. We've seen how to, for the simple linear regression model, do some simple checks, but for now we're just going to assume that that has been satisfied. So next we set up our hypotheses. Under the null hypothesis, we are assuming that all of our parameters are equal to 0. And then under the alternative, we say at least one differs. From 0, that is. All right, so now what we're going to do is we're going to look at our output, and we're going to find this value. So going up here to our output, remember in the R output, if we look for our F statistic, we find it right here with our p-value. Notice that the F statistic does give us our 2 different degrees of freedom. So in a publication, when giving your test statistic, you often do want to give both those degrees of freedom. But our F statistic in this case is 2.714. And then we also need our p-value. So notice our p-value is 0.048. And again, I'm going to use our 5% significance level, but there is that change in publication where instead of, just saying things are significant at the 5% level, there is a change. You just report the p-value directly. And we can see here, this is a case where our p-value is very close to that 0.05 level. So at the 5% significance level, we can conclude that there is a difference in mean infection risk for the 4 regions. All right. So that's how we would look at a model with a single categorical predictor variable. Now we could do things just like with the ANOVA, where we looked at the difference between the two, or between potential pairs of regions. So for example, we could look at, sorry, let me go back up here, make sure I don't misstate these. We could look at west versus south, west versus northeast, west versus north central, and so on. The only difference is now we would actually do that using the confidence intervals for the individual betas, because notice that those betas, so for example, beta 1 actually represents the difference between the mean for the west and the mean for the northeast. Now we don't have to stop at one categorical variable. We can definitely look at models with more than one, and eventually we're even going to see how we could look at models with categorical and quantitative. But for right now, we're just going to look at a model with 2 categorical independent variables. So we're going to extend this model, and so we're first going to consider what we call the main effects model. This is the model in which the 2 independent variables affect the mean response independently of one another. So this is going to be very similar to when we looked at a main effects model for 2 quantitative variables. So example, most ambulances have diesel engines. An engineer wishes to model the performance of a diesel engine as a function of type of fuel and engine brand. And so this example comes from the textbook given here. All right. So we've got 3 different fuel types we're going to consider. They are denoted F1, F2, and F3. And we have 2 different brands of engine. We're going to denote them as B1 and B2. So we are going to let F1 and B1 be the base cases. Okay. So we need to set up some dummy variables here. Notice that the fuel type has 3 different levels, so we know we're going to need 2 dummy variables for the fuel. So I'm going to let x1 be equal to 1 when we have fuel type 2 and 0 otherwise. And x2 is going to be equal to 1 when we have fuel type 3 and 0 otherwise. And then notice since brand has 2 levels, we just need a single indicator variable for it. So we've got x3 is equal to 1 when we have brand 2 and 0 otherwise. All right, and so notice here we have a picture of what this could potentially look like. Notice we are representing these with 2 different parallel lines. And again, the reason that we've got those 2 different parallel lines is because we are assuming that there is no interaction between these 2 categorical variables. So we could write out a model to predict diesel engine performance. And since we're assuming no interaction, here we would say the expected value of y is equal to the intercept, beta 1 x1, plus beta 2 x2, plus beta 3 x3. Now, notice that, again, this looks very similar to the model that we looked at with no interaction with quantitative variables. So if you were just to give this model and not give any context, a person would not know that these are different dummy variables actually only representing two categorical variables. So this is one reason it's so important to say what x1 and x2 and x3 represent for clarity, because otherwise a person would not know that this is for two categorical versus, potentially three quantitative variables. So let's consider all 6 possible combinations of fuel type and brand. Alright, so for example, we could have fuel type 1 and we could have brand 1. Well, let's look at what happens to our model. Remember that when we have fuel type 1 and brand 1, those are our base cases. So in that case, x1, x2, and x3 are all going to be equal to 0. So we get x1 is equal to 0, x2 is equal to 0, and x3 is equal to 0. So if those are all equal to 0, then we see the model just becomes the intercept. Let's look and see what happens when we have fuel type 2 and brand 1. So notice in this case, x1 is equal to 1, x2 is equal to 0, and x3 is also equal to 0. So here we're going to have the expected value of y is equal to beta naught plus beta 1. When we have the third fuel type and the first brand, this time we're going to have x1 is equal to 0, x2 is equal to 1, and x3 is equal to 0. So here we have the expected value of y is equal to beta naught plus beta 2. And we could keep on going, and I'll write out what these are and you can confirm these on your own. Alright, so notice one reason it's so important to keep in mind that we're working with dummy variables here. In other words, x1, x2, and x3 can only take the values 0 and 1. If we write out the 6 possible combinations, we actually see all the possible values that this model could take. And again, that is because we have these dummy variables. We don't have quantitative variables here. Also, what this shows us is essentially what we're getting here is we're getting different lines or different values for each of these 6 possible combinations. So when 2 independent variables affect the mean response independently of one another, we obtain a type of pattern seen in that graph above. So in other words, we end up with these segmented parallel lines that we see right here. So again, this goes back to this idea, when you have variables that are independent, you're going to end up with parallel lines. Well, as you probably could guess, if we look at the interaction, we're no longer going to have independent lines. So here is the summary of the main effects model with 2 qualitative or again categorical independent variables, one at 3 levels and the other one at 2 levels. And so notice here what you could solve for is the interpretation of those model parameters, and they end up being something fairly similar to what we saw when we had the single categorical variable. However, if the 2 qualitative or categorical variables do not affect the expected value of y independently of one another, then the response function may appear as below. So notice here they intersect one another. So in this situation, the response function differ for each brand. This means you cannot study the effect of one variable without considering what level you are at the other one. So in other words, when we think of this example, we had 3 different fuel types and 2 different brands. What this is really saying is which of those 3 fuel types is better is going to depend on the brand of engine. So it's not the same for the 2 different brands. It may be that when we look at brand 1, fuel type 2 is better, but when we look at brand 2, for example, it might be that fuel type 1 is better. And so this is the reason when we talk about categorical variables, just like when we did with quantitative, that it's important to consider these interaction terms. So we allow for this interaction by including the interaction terms in the main effects model. The terms will involve all possible two-way cross products, so this is going to be slightly different for each of the dummy variables. So what we're going to do here is we're going to write the interaction model to predict engine performance. So here we've got the expected value of y. I'm still going to write in all my main effect terms just like we did before. But now I have to write in my interaction terms. So this is where we've really got to go back and think about what are our categorical variables that we're interested in. I've got my 3 levels of fuel type and I've got my 2 brands. So my interaction terms are going to be as follows. I'm going to have an interaction term x1 and x3. Remembering that x1 was one of my potential fuel types, and x3 dealt with brand, and I'm going to have beta 5, x2, x3. And again, this is because this is for the second fuel type and brand. So be careful here. If you were just looking for patterns, the next thing you might say is, well, if I've got an x1 and an x3 and an x2 and x3, I need an x1 and an x2. But you got to remember that x1 and x2 both deal with fuel type, so you can't have 2 different fuel types that are interacting with one another because those belong to the same categorical variable. So here is the summary of that interaction model with the 2 qualitative or categorical independent variables. Again, one at 3 levels and the other one at 2 levels. And then here are the corresponding interpretation of the model parameters. And again, this is very similar to what we saw before.